So we need to talk a little bit about optics and give you some hints on how to solve some of the problems related to mirrors. Geometric optics can be used when the wavelength of light is smaller than whatever the object is that it's interacting with. We don't have to deal with the wave effects. So we have some nice, easy ray diagrams and math that goes along with mirrors. Some important vocabulary for understanding what's being spoken about in the notes is the difference between a virtual image and a real image. A virtual image is going to be an image that can't be projected onto a screen, and so it's going to be like the image you see in a bathroom mirror. You can't really project that on a screen. There are different shapes of mirrors and also lenses that will produce a virtual image. A real image is one that can be shown on a screen. Object distance and image distances are going to be used for both mirrors and lenses. The object distance is simply the distance between whatever the object is that is being reflected or imaged, the distance from that object to the mirror or lens. And the image distance is going to be the distance from the image to the mirror or lens. Plane mirrors are exactly what they sound like. They're the flat mirror, like any of the mirrors that you use in the room that do not magnify anything. The image is going to be the same size. It's going to be the same distance behind the mirror as the object is in front of the mirror. And you can use ray diagrams to locate the image by imagining two rays coming off of a point and going to whatever the observer's eye is, and then extending those through the mirror to the other side. Once again, the object height is the image height, and in this case the image is a virtual image because it appears upright and behind the mirror. The object distance is equal to negative the image distance. So when we talk about behind the mirror, we're talking about negative distances. The spherical mirrors are a little bit more interesting. There's concave mirrors and convex mirrors. We're going to assume small angle approximations that we have a focal point where all of the rays can converge. So we have a concave mirror, and that's where the reflective surface is on the inside of the sphere, and the convex mirror where the reflective surface is on the outside of the sphere. So the focal point is the point where all of the rays converge after being reflected. And the focal length is the distance from that focal point to the surface. You'll also notice that there's a center of curvature that's going to be basically, if you can imagine the mirror being a full sphere instead of just a curved surface, that would be the center of the sphere. And then we have a vertex that is along the optical axis, which divides the mirror in half, and it's where that axis intersects the mirror. So we'll start with concave mirrors, and I'm going to walk you through how to draw all of the rays to find an image. So you're going to choose a point on an object to image, and a lot of times the easiest way to do this is to just assume everything you're imaging is going to be an arrow and start at the point of the arrow. That means that the other point you need for the image, because it takes 2 points, can be where the object intersects the axis. So your first ray is going to go from that top of the arrow straight parallel to the axis into the mirror. It's going to follow the law of reflection, and it's going to reflect through the focal point, and you continue it on. And then the second ray goes from that top of the arrow through the focal point into the mirror, and it's going to come back out parallel to the axis. A third ray goes from the object through the center of curvature into the mirror, and because it's the center of curvature, it goes right back out following the way it came in, but it will intersect the other two. So now you have 3 rays that intersect at a point to reflect the top of your arrow. And the fourth ray is is useful, especially if you're given certain aspects of the problem. This could be used more like a geometric rule. That fourth ray that's going to go from the top of the object to the vertex of the mirror is going to reflect back out and go through that convergence point also. So from the point of convergence, you can draw the top of the arrow, and then it goes, in this case, it goes upwards towards the axis where the bottom of the arrow is. So when you're describing this image, it's going to be reduced in size. It is a real image. It is inverted, and it is also in front of the mirror. Now, convex mirrors are a little bit more complicated because those rays are not going to converge in front of the mirror. They're going to converge behind the mirror. So you're going to follow a similar path to get 2 or 3 lines that intersect, but you're going to have to continue them behind the mirror. So you continue the reflected ray back behind the mirror, which is shown with dashed lines, to a point of convergence. And in this case, our image is upright, so it's virtual, which means you can't project it. It is reduced in size, and it is behind the mirror. There are some important sign conventions for keeping track of in front of, behind, and some of the image distances and things like that. So we've got positive focal length for concave mirrors and negative for convex mirrors. Image distance is positive for real images, negative for virtual images. Height is positive above the axis, negative below the axis. And magnification is positive for an upright image and negative for an inverted image. And if you look at a diagram of any of the mirrors, those distances and the negatives and positives should make some sense. And then finally, 2 very simple equations. We've got the mirror equation, which is 1 over the object distance plus 1 over the image distance is 1 over the focal length. And finding magnification can be either be done with height or distances. So you can use whichever information you have. Signs do matter. So if you've got a negative image distance or a negative height, make sure you plug those into the equation properly. All right, bye-bye.